line A, line B, and line C. In the star connection, we have an opportunity called neutral. So this is the neutral. The problem is when the current flow through the conductor, it has to flow from positive to negative, higher potential to the lower potential. So here the neutral actually plays the part to allow the current to flow to the system. Just like from the mains power socket we have three conductors in the plug. One is for the phase, another is for the neutral, and third is called earth. That means in the case of short circuit or something goes wrong, the current would flow to that terminal. It will protect the equipment and to the circuit breakers. So in the star connection, you have three separate impedances. We call it ZP. Now you might be thinking why these all are the same. ZP is the phase impedance and all three impedances are same. If all impedances are same, that means the system, the star connected system, is balanced. But if all three impedances are different, or any one of them is different, is called unbalanced system. So for example, there are three separate rooms. Each room has different air conditioning, heating system at different power rating. You are going to supply three separate conductors to each room, and each room will consume power differently. Therefore, the impedances would be different, and we call it unbalanced system. If the load is balanced, means all impedances, loads are equal, we call it balanced system. And if the connection is star, we call it balanced star connected system. Now in the star connection, there are two types of voltages. One is called line voltages. Second is the phase voltages. So in the single phase system, when we talk about 240 volts or 230 volts RMS supply, that is your phase voltage. The line voltage applies to three-phase system, and it is defined as the voltage between two lines. The line A, line B is called line voltage between line A and line B. The line voltage between line B and C can be called VBC. The line voltage between line C and A called VCA. So we have three separate line voltages, and the line voltages are different to the phase voltage, because the phase voltage means the voltage across the load. We call it phase voltage. So there will be three phase voltages, and the phase voltages, like the 230 volts that we receive from mains power circuit, has the phase and the neutral. So the phase voltage means is the voltage between a line, let's suppose line A, and the neutral. So there will be three separate phase voltages in the star connection. That will be VAN, means the voltage between line A and neutral. VBN, the voltage between line B and neutral. VCN, the voltage between line C and neutral. Now, in the star connection, we have the derived equation to convert between the line voltage and the phase voltage. So, if you want to calculate the line voltage from the phase voltage, all you have to do is to multiply square root 3. In other words, the line voltage is equals to square root 3 times the phase voltage in the star connection. In the star connection, the line current and the phase current are equal. So it can be seen the current IL is the same current as IP. In other words, the line current is equals to the phase current. But the line voltage is equals to square root 3 times the phase voltage. Now this is the initial part of the star connection. What I really want to mention now is these two equations need to be applied whenever you are interested in calculating the magnitude. For example, 230 volts. So if I were to calculate the voltage that I am receiving from the mains power socket is 230 volts, what would be the line voltage? So that would be 230 times the square root 3. The line voltage is approximately equals to 398.87 volts. So if I say 240 multiplied by square root 3, because some might be receiving 240 volts within the tolerance, then your line voltage is 415 volts. So 415 volts is your line voltage, and your phase voltage, for example, is 240 volts. But it does not give us the complexity that we are interested in, for example. It did not give us any angles. At what angles the phase voltage would be? Which phase voltage? Which line currents? Because there are 3 separate line voltages and 3 separate phase voltages. 3 line voltages are VAB, the voltage between line A and B. Similarly, VBC and then VCA, 3 line voltages. And we have 3 phase voltages across the load. VAN, the voltage between line A and neutral, VBN and VCN. And if we want our answers or conversion with angles, then this fundamental equation will not give you the full picture. It only gives you the magnitude. I have already discussed about the difference between unbalanced and balanced system. In this lecture, in this learning outcome, we are focusing on balanced system because it would be easier for us to practice the equation. But of course, if you change the impedance, then it is possible to do the fundamental calculation. In conclusion, the line voltages in the star connection, and the line voltages are equals to square root 3 times the phase voltages. The line currents are equals to the phase currents. All line voltages are 120 degree with respect to each other. Line voltages are usually, by calculation, you don't need to remember it, but it's good to know. Line voltages by calculations are 130 degree ahead of the respective phase voltages. Now this point number 4, you would realize when you actually do the calculations. The angle difference between the line currents and the corresponding line voltages would be either 30 degree plus minus particular angle. Again, you don't need to remember this point because this comes with a practice. I will talk about the power representation in star and delta later on, because this is the summary of the balanced star connection system. So I would leave this point at the moment because we still have to practice the 3 line voltages and 3 phase voltages with an example question. So these 3 points, the true power, apparent power, reactive power, will be discussed later on within this video lecture. Now, like I said, that this 415 or 240 volts doesn't make sense because our voltages and currents and impedance, everything should be in complex form. So, in order for us to calculate the line voltage between line A and B, we need to subtract the 2 phase voltages. So, if you want to remember the equations, this is how we can remember it. VAB is equals to VAN, the voltage between line A and neutral. So this is a phase voltage, minus VBN. Now look at here, A and B, the neutral. VBC, if you want to calculate the complex representation of the line voltage between B and C, that would be VBN minus VCN. So BC, same negative sign.